Greetings, everybody. Let's continue our discussion of trigonometric integrals. And so in the last video, what we were looking at was integrating products of powers in sine and cosine, and we figured out what we could do if one of those powers happened to be odd. So if the power on sine was odd, we could make a u substitution with cosine. If the power on cosine was odd, we can make a u substitution with sine and use our trig identities to convert everything over. So now let's see what happens if we're in the case when both of those powers happen to be even. So now things aren't quite so straightforward, and that technique that we had before just kind of fails in this case. And it fails because if we take a power of cosine out, then we can kind of see what happens is that we still have our sine squared. We take a power of cosine out. Now we're left with a cosine cubed, a cosine of x dx. And so what happens if we say that this is going to be set up for my u substitution with du, now because that power is odd, when I take one of them away, then I can't use my trig identity to convert to sine anymore. Okay, that if the power was even, then I could divide that by 2. I could use my cosine squared is 1 minus sine squared, convert everything to sine, and go forward. In this case, since that remaining power is odd, I can't do that anymore. And so my technique from the previous video fails to work. And so what do I need to do? I need to come up with something else that's going to do the job in this case, that my technique fails, and it's pretty obvious why it fails in this case. And so we got to have something else. So what's going to help us out is that we need to recall some of our power reduction identities from trig. And those power reduction identities, if we had something like cosine squared, then we could, the power reduction identity that went with that was 1/2 plus a 1/2 cosine of 2x. Now, where did that really come from? This really came from our double angle formula, where if we first figured out what the cosine of 2x was going to be, and so just to kind of maybe refresh your memories a little bit with that we had the cosine of 2x just being our cosine squared minus our sine squared. And from there, we could either make this, we can convert this fully to 1 minus cosine squared for that one, and 1 minus cosine squared, to then come up with our formula so this becomes our 2 cosine squared of x minus 1. If we then solve for cosine squared, that gives us our power reduction formula. And so just kind of refresh your memories a little bit on maybe where that's coming from, and also kind of from the flip side of that to recall that we've got a power reduction formula for sine as well, so that our sine squared of x, coming from our other double angle formula involving cosine, was a 1/2 minus 1/2 cosine of 2x. And so in this case, what we're going to do is kind of put these two trig identities to a lot of work in kind of simplifying these integrands and taking things down from there. So let's take this example and see what we can do with it. And so one thing that we can do with this integral Since both powers are even, we can look at our power reduction formulas for each one of those. So our power reduction formula for sine squared gives us a 1/2 minus a 1/2 cosine of 2x. And the cosine to the fourth we can write as cosine squared dx. So that then in turn doing a power reduction formula for that one, we've got a 1/2 minus a 1/2 cosine of 2x and a 1/2 plus 1/2 cosine of 2x squared dx. So things look a little bit better. So now we've got it in terms of cosine. We can multiply this out. And so if we multiply this out, what we end up with, so what we get if we expand that, kind of looking at this, we've got a 1/2 minus 1/2 cosine of 2x, a 1/2 plus a 1/2 cosine of 2x. And we've got two of those, so we've got a 1/2 plus a 1/2 cosine of 2x dx. Now, this gives us a difference of squares in the first two, so those are easy to multiply together. So that's just going to give us a 1/4 minus 1/4 cosine squared of 2x times a 1/2 plus 1/2 cosine of 2x dx, which we can then just multiply those out. And what I'm going to do is I've got a one common factor of 1/4 in the first factor, a 1/2 in the second factor. So let's pull that out. 1/4 times 1/2 gives us a 1/8 out front. And so what we're really multiplying is 1 minus the cosine squared of 2x and 1 plus cosine of 2x dx. So if we multiply these together, what happens whenever we expand those? So we've got our 1/8, our integral, 1 minus the cosine squared of 2x, 1 plus the cosine of 2x, and we expand those. So we're going to get a 1 plus cosine of 2x minus a cosine squared of 2x minus a cosine cubed of 2x dx. So the idea is we expand that out into powers of cosine. So now, kind of looking at each piece individually, what we have is, so this part is just a constant and a power of cosine. So that one, okay, is easy to do. We know how to do that one. Our cosine cubed, we've got an odd power of cosine. So we've got our technique from the last video. So our technique from the last video, to be able to do, we could use that technique to reduce this. So now what is left over? Well, what's left over is this power of cosine squared. And for that one, we've got power reduction again. And so for this integral, we now kind of break it up into kind of three parts. We've got the integral of 1 plus our cosine of 2x dx. That's 1. And then minus a 1/8, the integral of our cosine squared dx. And then minus our 1/8, the integral of our cosine cubed of 2x dx. And so we kind of can treat each one of those cases kind of individually, and then go from there. So what happens with this first one? Well, the first one is easy. That's just going to give us an x and then plus a 1/2 sine of 2x for that integral. So again, kind of thinking about a derivative of sine gives us cosine. The chain rule, we bring out the factor of 2 to cancel out that 1/2. And so the first integral, okay, that one's easy to do. For the second one, we do our power reduction again. So our power reduction is going to give us a 1/2 plus 1/2 the cosine of double the argument. So 2 times 2, now we get a cosine of 4x dx in there. And then finally, our 1/8, the integral of cosine cubed 2x dx. Okay, and so with that one, kind of brings us to that next step. Let's kind of clean that up a little bit so that it looks a little bit more like our 2x that's supposed to be there. So we've got this expression. So now for our second integral, this one again becomes easier to do now. We've done the power reduction formula on that one, so we can simplify that. So let's kind of keep this process going. Okay, so where we were at, we had the 1/2 x plus 1/2 sine 2x. Then we had a minus 1/8 the integral of 1/2 plus 1/2 cosine of 4x. So we can take out that 1/2 again. So we've got our 1/8 x plus 1/2 sine of 2x minus a 1/16 the integral of 1 plus cosine of 4x dx, and then minus a 1/8 times the integral of cosine cubed of 2x dx. So for the second integral, we can integrate that one. So now that one becomes easy to do. So we've got a 1/8 x plus 1/2 sine of 2x from our first one, minus a 1/16 x plus a 1/4 sine, a 1/4 sine of 4x. And then we've got our last integral, our minus 1/8 integral of the cosine cubed of 2x dx. So we've gotten most of our integral done. So now that we've got something down that's a power of cosine cubed, at that point, we can apply the techniques from the previous section. So let's see how that one might work. So then just kind of singling in on what if we had the integral of cosine cubed of 2x, how would that go? Well, remember the idea was that we took one power out. So we had a cosine squared of 2x, and then we had a cosine of 2x dx. And we were going to do a u substitution with u equal to sine, and with that one. So if we then convert the remaining powers, that's going to give us the integral of 1 minus sine squared of 2x times the cosine of 2x dx. So now if I let u equal sine of 2x, du becomes 2 cosine of 2x dx from my chain rule. And so what my integral then becomes is a 1/2 integral of 1 minus u squared and du for that one. So this integral, again, becomes easy to do. So I get a 1/2 u minus, and minus a 1/3 u cubed with that one. And then our plus c. So if I kind of go back to my original function now, so if I go back to my original variable x, what do I get is a 1/2 sine of 2x minus a 1/6 sine cubed of 2x plus c. And so to kind of bringing this all together into our kind of final answer, what do we have? And so kind of coming back where we started, we originally had the integral of sine squared cosine to the fourth. In that, we used our power reduction formulas and expanded out to get a 1 plus cosine 2x minus cosine squared 2x minus cosine cubed of 2x. And then we'd split that up into 3 different integrals with 1 plus cosine 2x, cosine squared, and then our cosine cubed. So our 1 plus cosine 2x gave us just our x plus sine 2x. Then we had, for the cosine squared, we used power reduction again on that one to give us something we could integrate to obtain x plus 1/4 sine of 4x. And then finally, for our cosine cube, we used the techniques from the last section, from the last video, to obtain 1/2 sine 2x minus a 1/6 sine cubed 2x plus our arbitrary constant. And so from there, we could go a step further and use some algebra to simplify that. But we've actually gotten the integral in that case. And so kind of one thing that I want you to take away from this is if both of our powers of sine and cosine happen to be even, now we're using power reduction and we're then kind of multiplying everything out. We may continue to use power reduction for when we have powers of cosine, even powers of cosine. If we've got odd powers of cosine, we've got the techniques from the previous video to fall back on. And so things get a little bit messier when both powers happen to be even, but we're still just using our power reduction formulas. We're kind of hammering things away and kind of using other previous things. So maybe we'll do another one of these to kind of see another example of what happens whenever both powers happen to be even. But this gives you a pretty good introduction to how things can go in that case, and I will see you guys next time.